Welcome back to the lecture series on electric drives. So in this lecture, we are going to discuss about scalar and vector control of induction motor drives. Before we look at scalar and vector control of induction motor drives, let us recollect about the DC motor control, constant torque and constant power region. We all know very well in constant torque region, the flux has to be retained to maximum rated value. So if this is a constant rated flux, torque is directly proportional to the rated current. So if we want to have rated motor torque, we can load with rated current. When it comes to constant power region, okay, we know very well above this rated speed, all the rated values like EB, back EMF, as well as current are to be retained to the rated value. If keep on increasing, as speed is increasing, if you keep on increasing EB above the rated, it would cause damage to the motor drive. So above this rated point, we know very well, we have discussed in the class, the back EMF and the current are supposed to be retained to rated value from this point onwards. So if you retain from this point onwards constant rated back EMF as speed is keep on increasing, from this equation we can see as speed is kept on increasing, and this has to be retained to rated value constant. So the only one way that we have to achieve this one is to reduce the flux, hence the name it's called as field weakening. So in a simple way to say, below the rated speed the flux has to be maintained constant, and above the rated flux has to be weakened, that is field weakening region. I hope we need to keep this picture clearly for the further discussions. So below the rated, it should be maintained as a constant rated flux, and above the rated speed we need to go with field weakening or flux weakening. Right? Now keeping this in mind, let us go to the induction motor drive. So in induction motor drive, how can we control the motor drive? We can control the induction motor in two ways. One is by scalar control, another one by vector control. So in simple words, we can understand scalar control. Scalar control is nothing but which relates to control of only the magnitude of any variables. Okay, we have taken the fan example most times in the class, okay, where the regulator was there to vary the voltage. By varying the voltage, the magnitude RMS value of the voltage, the rotation speed of the fan was changed. Okay, the fan speed is controlled by the regulator. So we are changing only the magnitude of the voltage. So such kind of controls are called as scalar controls. Scalar controls means only magnitude is controlled. However, in induction motor drive, we also understand that it is a three-phase system, and we have a rotating magnetic field which is the resultant of the three magnetic fields produced by three-phase system, okay, where the magnitude as well as position of the flux is also very important. So basically in two ways we can control the induction motor drive. So let's look what is scalar control for a while, then we'll go understand a little bit more into vector control. So in simple words, scalar control relates to the magnitude control of a variable. Vector control relates to the control of magnitude as well as the position, at what position the magnitude will be. Right? So we'll be considering that. That's called as space vectors. So we'll look what are those in coming lectures. Now let us go to the scalar control only for a while, understand a little bit of that. And we have discussed in our class induction motor. Induction motor basic torque equation. Yeah, we can see in the screen. Okay, the torque is proportional to slip as well as square of the applied voltage. Okay, So inverse to the synchronous speed and all that thing we have already discussed in the class. And how do we get this starting torque? So starting torque is nothing but at standstill when speed is 0, motor speed is 0. So what is slip? Ns minus n divided by ns. So ns by ns, slip is equal to 1. So at starting, we have discussed in the class also, at starting s is equal to 1, put s is equal to 1, you will get this equation. So starting torque. Now also we have discussed, we have derived for maximum torque. So the maximum torque appears to be when slip is equal to R2 by X2. Putting that R2 by X2 slip value, we'll get this equation. That means maximum torque is proportional to square of the applied voltage. And likewise, when the motor torque equation is referred to the stator side, okay, through equivalent circuit, that would be equation will be in this way. Okay. Now, what we can observe here is that, for example, I want to vary the maximum torque. Okay. So how do I vary? If the applied voltage I have reduced to half, my torque maximum torque reduces because it's a square times of that one fourth of the maximum torque. So here there is no significance of any position or anything. It's only magnitude of V2. Just reduce the magnitude of V2, the torque will be reduced. That's the meaning of scalar control. Keep this in your mind. Now let us see scalar control by varying stator RMS voltage and fixing frequency. I already told you, when it comes to AC systems or AC drives or anything, so it's not only the voltage but also we need to consider frequency also. So voltage and frequency is the fundamental component of AC systems. So in this case, what we'll do, we'll fix the frequency and vary the RMS voltage. Applied RMS voltage, by varying applied RMS voltage, we can uh, um, fixing the frequency, that we can see. Now what would happen with this kind of control is that, for example, let us see, if I reduce the applied voltage to half of the applied voltage, typically one fourth of the Tmax has to come. Tmax is around 1, it has reached to 0.25 around, so it has reduced in that way, one fourth time, as I told you earlier. So the characteristics would change with the applied voltage in this way. What do we observe from these characteristics? As I have reduced the applied voltage, your Tmax is reducing. That means maximum torque ability is reduced, as well as your starting torque also reduces. So by just varying RMS voltage for any induction motor drive, okay, your maximum torque ability will be reduced and starting torque ability will be reduced. And what do we find problem with respect to just varying RMS voltage is that the speed range that you get here, control over the wide speed range is not possible. Okay? So such kind of control are very feasible to fan kinds of load, pump kind of load. Okay. From this characteristic, we can see the operating points. When we see the operating points, working operating points, this curve indicates typically torque is proportional to square of the voltage. So we know very well quadratic load. I hope that we can remember types of load. Torque was proportional to square of the speed. Which kind of load that we have discussed? It's a quadratic load, and examples for that one is fan and pump. So in this case, from the characteristics we can observe by varying RMS voltage, this can be typically used directly for fan and pump kind of loads, because we know very well as fan is rotating at low speed, the torque requirement also, the thrust requirement is also very small. So that's what torque is proportional to square of the speed. So as speed is low, torque is also low. As speed keep on increasing to rated value, rated point, it will go to the rated torque. So such kind of loads, so fans and pumps load, so this can be directly used, and that's what we can see fan regulator RMS voltage will change, fan speed will be changing. So this is one of the best example for just varying RMS voltage, fixing the frequency. How about second combination possible? So why can't we fix RMS voltage, applied RMS voltage, and vary the frequency? How the characteristics is going to change? We can see that from the characteristics, as above the rated frequency, that is rated speed, if I keep on increasing my frequency, the characteristics will be diminished, right? And due to this, during the low frequency, it may go to high values of torque. The torque characteristics will go in this way, right? So that would cause higher torque requirements, means higher current requirements. Higher current requirements means you are going beyond the rated values. That would cause the damage to the motor drive. So applying at low frequency, just a frequency with fixed RMS voltage, will cause damage to the motor drive. So hence this frequency control is preferred above the rated torque, and above the rated speed. Above the rated speed, we can see the characteristic nature is inverse characteristic nature, which is nothing but constant power kind of nature we can see. So below the base speed, you're not applying any only frequency control. Only frequency control would cause the damage, and above the base speed, frequency control is a good kind of nature where we can torque is inversely proportional to the speed of the motor drive, because we know very well frequency and speed are correlated. Ns is equal to f by 120 f by p. If you half f, that means ns will be half. If ns is half, the rated the working speed of the motor drive is also half. So that is the way. If f is increasing, ns is increasing. So ns is increasing, speed also the motor drive is going to increase, induction motor with the slip, right? So in simple words, above the rated speed, frequency control will give us the inverse characteristics of torque and omega. So also called as constant power region, right? Now what are we going to do below the rated speed? If the frequency is changing, we are getting good speed characteristics. Unlike here, by changing RMS voltage, you are getting only less speed range, okay, and but your torque capability is reduced. Whereas by increasing frequency, getting very easily all the characteristics of speed. However, in low speed and below the rated, the current torque will be high and current drawn will be more. So what we will do below the rated speed? So as keep on changing frequency, you can see the frequency, as frequency changes, your speed is also going to change. Let us look back to the below the rated speed, varying both stator RMS voltage and frequency. So we know very well that we have applied a sinusoidal voltage and sinusoidal currents are produced. Sinusoidal currents results into sinusoidal field. And we know back EMF. What is the back EMF equation? So let's understand the applied back EMF voltage is nothing but the induced voltage in any coil is N times d phi by dt, rate of change of flux. This is a basic Faraday's law, right? So the amount of induced voltage in any coil is directly proportional to the rate at which the flux is going to cut, d phi by dt. So applying that one here, n is number of turns, so d phi by dt, so taking the differentiation of that one, so omega phi m cos omega t. So let us consider the magnitude of this one, right? So that's a peak value. The peak value is nothing 2 pi n f into phi m. Phi m is the rated. So this entire thing is the maximum. So this is a maximum. We know very well AC quantities. So peak divided by square root 2 is nothing but your RMS quantity. So applying that one, the final equation will be 4.4 times of n. N is number of turns. This also will be constant for typically one design already done. So F times of F is frequency and pi is the rated flux. Right? So ERMS proportional to flux into frequency. So that's what we can see. And what did we, at the beginning of the lecture, what did we observe is that below the rated speed, flux has to be maintained constant. Again, I will repeat. Below the rated speed, flux has to be maintained constant. Right? So from this equation, what we can see is ERMS, F and phi m. As I am increasing my speed, that means increasing F, I will increase my speed. Below the rated speed, we need to maintain flux as a constant. So in order to maintain this flux has to be constant. If I keep increasing F, E also should be increased. So that is E by F, that is volt by frequency, applied voltage, RMS voltage, and the frequency. Ratio should be maintained constant to maintain the constant flux. Again, in simple words, to maintain this as a constant, E by F ratio should be maintained constant. So that's what this name for this control is called as V by F, volt by Hertz control. Right? So by this, what will happen? Flux will be maintained constant to rated value till the base speed. Now what we will do? Apply adding this one below the rated speed. This is fine. V by F control we have done below the base speed. So what we will do? We'll combine above the base speed frequency control and below the base speed V by F control. So we can see that V by F control we are getting maximum rated torque capability and inverse torque characteristic above the rated speed using frequency control. So in simple words, below the base speed V by F control, above the base speed frequency control. So combine this two, what will happen? We'll get something characteristics like that. So you'll be changing only frequencies, frequency as well as voltage in this region, and above the rated speed you are just changing the frequency. Right? So this is what the characteristics look like, and this is what we demand. Most of the tribes demand this one. That's what we have seen at the initial part of the lecture. Right? So below the base speed, it has to be V by F control to maintain constant flux, and above the base speed, it should be frequency control to have the field between region. I hope this is. So what we see here is scalar control. We are just changing the voltage magnitude, right? The magnitude of the variables, for example, voltage and frequency. We're changing the magnitudes of them. So that is the meaning of scalar control. Right? Now, how do we get closed loop of this one? This is an example for that one. Same thing. Constant torque region as well as constant power region. So how do we get the closed loop speed control? Okay, we know very well. So any control, we say speed control means I'm sensing speed. Right? So this will produce the PI controller, output will produce the control variable, and the control. The final way to get variable voltage and variable frequency is through inverter only. That we have understood. So by proper switching of the inverter frequency and the voltage, you will get the control of induction motor drive. So how do you get this frequency? Frequency is given by the controller. So we know the actual speed, and this will produce the slip speed. The slip speed and the actual speed, if you add, you will get the synchronous speed. Okay, this is like S times ns, and this is N. So if you do combine this one, you will get resultant of that one will be ns. Ns results to the frequency where it has to operate. Right? This is a complete closed loop operation of feedback control. This one example we can see. This is what we can see. AC voltage will be converted to DC, and through switching of the inverter, the voltage and frequency for the induction motor can be controlled. So this was one of my work. If you want to refer, you can go to refer. It's a closed loop drive, induction motor drive. So this was a simulation model that I built using Scilab. It's an open source software similar to your MATLAB. This was the entire closed loop operation system. So speed is sensed and it is processed in the PI. The PI control algorithm is built in the PC, and it will give the commands to the inverter. So inverter is maintained to the V by ratio. So that will be controlling the speed of the motor drive. So this is a closed loop operation. As we know very well, closed loop operation is whatever the command that you say, step change in speed, it will follow the step change in the speed. And here I gave 1000 to 1200. So this actually is practical speed that has been measured. So as well as I told you, any speed control means if you load with certain torque at that point, it has to resume back to the speed of the command. So I gave 1000 as a 1000 RPM. It was running at 1000 RPM, and we have loaded with torque, and we can see the controller is getting back to the required speed. Suppose scalar control. Scalar control, you're just changing the quantity of the applied voltage and the frequency. Voltage and frequency are changed, the variables. And in this we can see that scalar control relates to the only magnitude of the variable. Three types we have seen: by fixing frequency, RMS voltage is varied, and then fixing RMS voltage, changing frequency we have seen, varying both V by F we have seen, and then we understood the scalar control. What would be the drawbacks? Can we think on that for a while? Okay, I already told you, three-phase system, induction motor three-phase system is producing a three magnetic fields. The resultant of the magnetic field is our rotating magnetic field. Our magnetic field itself is rotating, and it has a magnitude as well as a position information. So magnitude and position, at what position, at what flux, what rated flux it is running, that's what it is. In the previous equations we have seen ERMS is equal to proportional to F times of phi m. Phi m was maintained rated. So the E by F, that is volt by hertz, is approximated to the flux. That means we have done approximately control, not accurate control of the flux. Keep that in mind. So there it is only by changing stator variables, okay, we are changing the internal flux, but we don't have direct access to the flux. We are not exactly controlling the inside variable with accurately magnitude as well as position. So what would be the advantage and disadvantage of this scalar control? It's simple. We are just changing the variable voltages, and then voltage and frequency from external through the inverter. We are just changing the voltage and the applied voltage and as well as the frequency. So it is easy, simple control. But since you are not controlling the inside flux accurately, what will happen is that, for example, I'm changing applied voltage, okay, and applied voltage should reflect the current, and that current should reflect the flux, and that flux should go to the resultant flux. So what we say is the sluggish response you will find. That means you're not controlling the inner variable very fastly. You're just controlling outer variables, and the dynamics will be slower. That's what we can see. So what would be the advantage and disadvantage of this one? So scalar control is simple to implement and offer good steady state. So no problem with the steady state. At steady state, it goes to steady state variables like V is maintained constant, everything, that's fine. So the transient part, that's what I'm saying. When you apply voltage, it will take certain time to go to the steady state change. So during this transient, the dynamics are very slow. So you're not bothered about the transient part. So it's very simple to control, scalar control, and as well as it offers good steady state response. And these are very simple. Most of the industry drives apply scalar control only, most applications. And you can see most of your fans that are rotating in your household or industries or anywhere, okay, they are applying VBK control. Your pump sets and everything that are applied, simple VBK control is sufficient there. Right? So understand that where exactly scalar control can be applied. Very simple. You don't bother about the performance and everything around it. So such kind of applications would go with scalar control. What would be the drawbacks? As I told you, dynamics are slow because the transients are not controlled. Keep in this mind, we are not controlling the transient part. Means we're not. We don't want something internal variables very accurately to control. So that's not possible in scalar control. And as I told you, air gap is approximately E by F. Is approximate. You're not getting. I told you, flux is a rotating magnetic quantity which has a magnitude and position. Here we are just bothered about the magnitude. If I am maintaining phi m by maintaining E by F ratio, V by F ratio, that is enough in a simple way. So it is kind of indirect nature. You're not controlling accurately. Approximately, you're putting that as a constant. So accurate control demand such applications like EV, electric vehicles, where flux is very important point. I think torque is also very important point. Such variables we are not controlling in scalar control. So torque is not controlled, right? So torque is very, very important point when it comes to certain applications like EV. For example, if the torque has more ripple on it, okay, what would it cause? It would cause vibrations, and that vibrations is not acceptable to the application for EV. So keep that in mind where exactly we can go. Now, scalar control does not provide us accurate control of the flux and does not provide directly control of torque also. We have not seen till now how the torque is going to control in scalar control. So I hope these all parts are understood what is meant by scalar control. In order to have better understanding, I've taken MATLAB simulation as an example. So for the scalar control, so let us see what this induction motor. So I've selected a 5.4 HP, 400 volt RMS, line to line voltage RMS, and 50 Hertz, 1430 RPM. That means if I give 400 line to line voltage at 50 Hertz frequency, the motor will run at 1430 RPM. Typically for this one, it will be around 1500 RPM synchronous speed, 50 Hertz, 120 F by P, a 4-pole machine. So that's what we can see. And from this, we can see calculate the rated torque also. 4 kilowatt divided by 1430 converted to RPS, and 4 kilowatt divided by that RPS will result into the required torque level, rated torque level of that motor. Fine. So this is what example we have taken. So that means if I give an AC supply with 400 volts and 50 Hertz, the motor should run around 1430 RPM, rated RPM. That's what we can run and see. Let us see what will happen. So scalar control, in the sense, I'm changing only the magnitude of the applied voltage and the frequency magnitude. So let us look what will happen with that scalar control. This is the simplest way if you get any motor or induction motor, right? So if you connect to the directly full voltage and full supply, it will run at the rated speed. Okay, it's almost reaching to 1435 RPM. So let me stop here. Let us look for a while inside what will happen. So this is the transient part, and it's going to steady state current, and it's going to reach the steady state torque. Everything and steady state speed also is going to be reached. Now what I'll do is that, what is meant by V by F ratio? So if I have to wait below the rated speed, I have to maintain into constant flux region. That means if I reduce F, then simultaneously I have to reduce E. That is the meaning of E by F ratio voltage. Now let us change the voltage and frequency to get that V by F control and to see this change in the speed. So what I'll do, I'll reduce frequency to 25. Nearly half of the speed of the motorbike. So until it is taking transients, so after the transients it settles over. After the transients, we can get the steady state value. So around 700, and you can see oscillations also. I open estimation credit. So earlier it was 1430 RPM. Now it's reduced to nearly around 700 range, near to 700. So that's why we are just changing the voltage as well as the frequency. That is meaning of V by control, and we can have the maximum torque with V by control. So that is what the V by control indicates, and the flux is maintained. These are things that we can see from the scalar control. So stop here. Now let us put one question. We have a AC supply, 400 volts, 50 hertz supply, and that we have given to motor. The motor will run at standard RPM, 1434 RPM, fine. So in order to have variable speed, we need to have variable voltage and variable frequency. But how do we get? We don't have a direct variable available, variable voltage and variable frequency to give to the motor. We have a standard voltage and frequency fixed given by the supply. So that is 400 volts, 50 hertz. And we have already discussed a lot in lab as well as in theory about the inverters. So inverters will help us to produce a variable AC voltage with variable frequency. So what we are going to see in the next example is, so what I'm going to do, the same motor I have kept. Okay, now from this DC I'm giving an AC through this inverter to the motor, fine, using this inverter, fine. So in this I have set in such a way that the frequency is switched to the period that I have set here is 50. Period is 0.02, 20 millisecond, corresponds to 50 hertz. Okay, so that's simple 180 degree conduction mode, and this also we have discussed a lot in the class. So that I'm going to give as an input to this motor, and let me run. So typically 400 volt RMS we are giving to the motor, and the frequency I told you is maintained with 50 hertz switching. So you can see around 1430 RPM it is running fine. This is line to line. So I'll stop here. Let us see, this is the line to line voltage. This is the line to line. Hope you remember 180 degrees. And this is 120 degrees positive and 120 degrees negative. Okay, that's what we can see of the line to line voltage. So the phase voltage will be the step 1. That was 180 conduction mode, simple. That I am going to apply to the induction motor if you're running. So let us see the torque as well as current. Using power electronics, we are switching. We are not finding exact the sine wave. So power electronics corresponds to harmonics. So that is one of the drawbacks that we have initially learned about power electronics. So we have a switched voltages and switched currents. So because of that, we can find the ripple on the torque also. So this is what we can see. However, since we need to have a variable, this is for the fixed point, it's okay, we can give a fixed supply from the supply itself. But we need an inverter. Why? Because we need to have variable. We need to have a variable voltage and variable frequency. What I'll do is that I'll reduce the frequency to half. Frequency to half means 25 hertz corresponds to 40 milliseconds. So that entire thing I'll just change here in the switching. I hope you all practiced this inverter. And here also switching. So I'm reducing the frequency here. And simultaneously, what I'm supposed to do is that I have to reduce the voltage. So this voltage, if I also need to make it to half. Right? So where does this voltage comes when regulated AC supply? AC supply is been rectified to DC. That DC, again you need a chopper to change that variable voltage. Okay, or using SPWM technique, you can vary the voltage and frequency in this inverter itself with fixed DC. So the two possible content. Now let us look at this. So we can find as it in the circuit, it will go to steady state value. So this is VBK control. How do we achieve VBK control? Using inverter. This is one of the preliminary simulations that you can try. You can do on your own self. The same motor that we use. So now, till now we have looked about scalar control. We understood that it is only the magnitude control. So by controlling the magnitude of the variable like voltage and frequency, we are able to control the induction motor, right? Speed. That was the scalar control, and we have taken one example from the MATLAB. So we have built the model and we have changed through the inverter. We have built the inverter and we have changed the voltage and frequency, and we have seen how the speed is going to change by VBK ratio as an example. Now let us come back to the vector control and let's try to understand what is meant by vector control. Scalar control relates to only magnitude. As I said at the earlier of the lecture, okay, vector control relates to what? Magnitude as well as position as space vectors. Right? And we have seen scalar control drawbacks. What was the drawback? The scalar control has deficiency of precision. It is not precise, and it has the sluggish response, low dynamics. That's what we have seen. Countering the scalar control issues, vector control has raised good level. So it is high precision and good dynamics. So that's what you can understand clearly. So what is meant by vector control? We are controlling magnitude as well as the position. The second thing is that they are preferred for high precision and good dynamics. Example like torque control of electric vehicle, so flux control of field oriented controls and all that thing we can see. In case of induction motor drive, we know very well it's a three-phase supply motor. So three-phase AC supply is given to the induction motor. That will produce three-phase current, that will produce three-phase flux, and that will interact and will produce torque. So here the torque production is dependent on three-phase system, and it is very hard to analyze the torque relationship or the flux relationship using the three-phase analysis. So we will do small vector analysis. That's what we call as vector control. So for that, what we need is a three-phase system is transferred to two-phase system. So that means, so let us see what will happen. Now in DC motor, we have known the torque is proportional to flux and the current. It's a quadrature components. Okay, so when you can control the torque by keeping the rated flux constant and varying the armature current. So it is a scalar quantity. Torque is proportional to flux and the current, both are scalar quantity. Whereas in case of induction motor, it's a three-phase system, okay? And the torque developed is also can be represented similarly to the torque developed with the DC motor, as we can see in this equation. Okay, phi s is a flux and is is a current. What is actually this flux? As I told you at the beginning of the lecture, in case of induction motor, the flux that we are going to see, phi s, is actually a resultant flux of all the three fluxes, and it is a position dependent, hence it is a vector. So phi s is a vector phi s and vector is. The torque is proportional to phi s and is. So we need to understand that resultant vector and the resultant vector of the current, resultant vector of flux, such that we can control similar to like a DC motor. And why? Because why we need this analysis? Because three-phase analysis is not so easy. That's what we'll do. We'll replicate the induction motor system into the two-phase system similar to DC motor control. That is what vector control means. So let us understand induction motor. So there are three-phase windings and I'm giving three-phase currents. Okay. These three-phase currents can result into resultant one, and I already told you rotating magnetic field. Okay. So the three-phase system will be having a resultant vector. That resultant vector will be rotating. Keep that in mind. So the resultant vector will be rotating. Okay. Now what we'll do, the first thing that we'll do is that entire three-phase system is converted or transformed into a two-phase 90-degree quadrature system. Okay. So this is beta and alpha and beta are indicated as a stationary reference frame. That means stationary three-phase system is transferred to stationary quadrature system. This is I alpha and I beta. So it is a simple mathematical graphical analysis. Okay. So we will take this in one of the axis along with one of the phase, and rest all are transferred to quadrature one as well as onto this one. The components are dropped into that one. So based on that component values and everything, for example, it's 120 degrees, 120 degrees, nothing but 30 degrees. So 90 plus 30, so it costs 130. So when you drop the component onto Q axis, A axis and onto the B axis, So you will find the mathematical representation. That's called Clark transformation. So Clark transformation is a stationary quantities three-phase system are transferred to stationary two-phase system. Just keep this understanding. Now, since this resultant vector system itself is rotating, so this axis also, the resultant vector of this quadrature axis also will be rotating. Hence, this entire entire 90-degree axis system is also will be rotating at speed. So everything quantities are in a rotating structure. So the stationary structure is three-phase to two-phase, and this two-phase will be again rotating. So that's rotating two-phase, that becomes DQ axis. So DQ axis is rotating frame, that's what we can say. And this AB axis, which is also called as alpha beta axis, is a stationary frame. Keep that in mind. Stationary reference frame as well as rotating reference frame. So the three-phase system is transferred to stationary, and that stationary will be transferred as a rotating vector. So by this, and it's same thing, dropping the rotating vector also components onto Q and A, P and A axis. Likewise, the three-phase vector. Now let us say the voltage equation. Voltage is equal to R into I plus d phi by dt flux. This entire equation. So we have a stator equation. Likewise, we have rotor equation. So this is the normal vector, rotating vectors. So the rotating vectors is transferred to dq, 90-degree rotating vector. The three-phase system, three-phase rotating vector is transferred to 90-degree quadrature rotating vectors. So that means three-phase currents transferred to IDQ, three-phase voltages are transferred to VDQ. Likewise, three-phase flux also reduced to phi dr and phi q. So the components can be reduced to three-phase one coordinates to two-phase. So by this, what will happen? The torque produced, the derivation after the results to the torque produced is a flux dependent component as well as current dependent component. So finally, it results to, okay, based on the magnetizing components and everything, flux and the current IQS. So this IQS, one of the quadrature component, okay, controls the torque. So IQS is required. It's the IQS that your system, that your result will control the torque, and IDS controls the flux. Now the same thing, the vector control now can be seen into the quadrature system, that can be reflecting us for the DC motor control. So IDS is nothing but IF field current, and IQS is nothing but your armature current. So keeping the field current IDS constant, flux will be maintained constant, and IQS, if you have a rated current, you IQS rated, then you will get produce rated torque. In simple words, so if you control IQS, you can control the torque. If you control IDS, then you can control the flux. This is what you have to understand. That means the three-phase quantities are transferred to two-phase rotating quantities, and these two-phase rotating quantities, if you are able to control either of them, it's a decoupled. You can control flux as well as you can control the torque. Now, as I told you earlier, in scalar control, we don't have the direct access to go to get the torque and anything. Now, because of this vector analysis, vector calculations, you can estimate the torque. That means earlier in our lectures, we had what is meant by speed control. You will give the reference speed and you will sense the actual speed. Then you are able to control that speed. Now what will happen in torque control also, when you go to inner loop torque control, you will get the reference torque, but where do you get the actual torque? So the actual torque has to be either sensed, which is impractical torque sensors, keeping torque sensors. So now it can be estimated. So it can estimate it from this equation by flux and IQS, the mathematical equations. You can estimate the actual torque. So when you have actual torque, you have a reference torque, then you can process. Likewise, by controlling IQs, you can control whatever the torque that you require. And you want to maintain flux. So maintain flux can be done by IDS. For example, earlier to the lectures, if you want to keep constant flux region, there is a two-part region. One is constant flux, another one is constant torque, constant power region, constant torque and constant power. In that we understood below the rated speed, we need to maintain constant flux that you can keep accurately in this, right? So that is IDS and IQs. Now the vector control of induction motor drive can be done in two ways. Okay, one is called as direct torque control. I hope that you understood by this time now. Now you are able to get into the torque and into the flux. That is more important, which is not possible, which was not possible in our scalar control. There we have approximately controlled the flux, okay, and we were working for the without control of the torque. Now we got access to the torque by the equation, and we got access to control which parameters to work for what. So that's what we have got into the vector analysis. So this is what helps us to control the torque and as well as flux. Now when you direct control the torque, so that means you give reference torque, you sense and estimate the torque from the equation, and that we are going to give the control to the IQS. If you control IQS, then you are controlling the torque. Okay, so that keeping we need to understand. And what is one field oriented control? You are controlling flux. So you can control flux as well as torque using vector analysis. That's what is vector control of induction motor drive. Now let us look into direct torque control, DTC. So as I told you, so in DTC, one of the primary thing is that from the DQ model, you are going to estimate the torque. So you see, you are taking IA and VABC. ABC quantities are transferred to DQ. Same voltage quantities will be transferred to DQ. And flux and torque, flux will be estimated first and then the torque will be estimated. So you got flux as well as torque vectors. Now you got accurate torque here. So now you give the reference torque and the actual torque is sensed, which was not possible in scalar control. So now this will be processed, and typically always it is preferred to have inner loop. With this outer loop, speed control will be there, that will give the reference torque, and that will be given to the torque controller. The torque controller typically here we are going to use is hysteresis. So in DTC it is hysteresis that is being used. So switching on and off, on and off, on and off with a band kind of that we can see. So switching table. Now why this switching table is required? Because as I said, you vector control. So the vector will be rotating from all the angles, all the 360 degrees. So each 360 degrees is decoupled into inverter, can be decoupled into 6 vectors, 60 degree, each 60 degree. So in each 60 degree, which are the things to be switched on and off? That is called as vector control. Right? So that's what switching, and switching pulses will be given to the inverter. So that is direct torque control. Now, any guess of what sort of problems might be here? Since we are using the torque hysteresis band control, it will have fixed ripple. So the fixed ripple will have, and the frequencies also will be variable frequency, unlike our switched fixed PWM pulses. Right? That's what the drawbacks of that. Now, what is meant by field oriented control? So in DTC, the problem is the torque ripple. Torque ripple will be there. That is an obvious drawback of DTC. If you want to have only direct torque control, okay, controlling torque, no problem, you can get in DTC. However, there will be certain ripple. Okay, So definitely because of the hysteresis control, they release certain ripple in the torque. That's one drawback of DTC. So overcoming all these difficulties, okay, field-oriented control was developed. So FOC, the abbreviation of that one is FOC. FOC has been solely developed for high performance motor applications where accurately you need torque and flux to be controlled, which can operate smoothly over wide speed range, can produce full torque at zero speed, which is most important for electric vehicles. Okay, at zero speed you need to produce high torque, and is capable of quick acceleration and deceleration. This is very important. So the dynamics should be very accurately controlled, quickly controlled. That's what is requirement. So field oriented control will help us in that. So in this also there are two types. Okay, one is direct field oriented control and another one is indirect field oriented control. So direct field oriented control is simple that it is used rotor flux vector. I told you the rotor flux vector amplitude and position is calculated directly from measured quantities. VABC, IABC is the very variable quantities that has been measured. From that directly you are estimating amplitude and the position of the rotor flux. Okay. Now indirect field oriented control, when I is used, rotor flux is calculated indirectly from speed. So from speed and slip estimations, and there is a current model, inverse current model. From that model you can, from that field control equations, you can calculate the flux as well as position. Here it is estimated from directly measured quantities of voltage. Here it is estimated indirectly through the current model. So DFOC, direct field oriented control. So you give flux command, you give torque command. So below the rated you can give the constant flux, rated flux. Above rated you can give field weakening. Right? So torque also you can give whatever torque demanded. What will happen in this direct field oriented control? From the motor voltages and control and the speed, you will directly estimate the flux and the rotor position. All these things are estimated directly. So now position is also very important in field oriented control, not only magnitude but also position. So in indirect field oriented control, okay, from the commands, required commands, slip frequency and estimate will be estimated, and from that the position information will be estimated. So there is an inverse current model that will be used in that. So you know what we can observe in compared to scalar control and vector control. Vector control needs vector analysis, okay, which is not that much feasible, not easy to do. So a complex control. Vector control is a complex control. However, complex control, it demands for certain applications like EV, we need high performance. So such kind of applications, we need to go with vector control analysis. So in this vector control, we have seen direct torque control, DTC, and FOC. Under FOC, we have seen direct FOC as well as indirect FOC. So let's have a small comparison of scalar and vector control. So scalar control, simpler form of motor control, and it is used for more versatile applications, from simple applications, fans and pumps. So good steady state response, poor dynamic response is a drawback, low performance drive, higher power dissipation. Right? Whereas vector control, complex mathematical model, precise control of AC motor. This is very important aspect, and excellent dynamic response. And they are used for high performance drive, low power dissipation, and these are used for very high performance applications like electric vehicles, tractions, and everything. So that's about comparison of scalar and vector control. Let us take an example of DTC control. So we can find AC4 space vector modulated DTC control as an example given in the MATLAB. So let us look into that one. What does it contain? How it's going to control? So look at the mask. You can see the three-phase AC is converted to DC. That DC is converted to AC, controlled AC through the inverter. That will be given to the motor. Right? And here we can see the DTC. DTC, what we can see, the speed controller will produce the torque reference, and that torque reference is given inside. So let us see inside the DTC control what are the things, and output of that one is the switching pulses that is being given to the inverter. This is the DTC. Let us go inside the DTC and see what is it contain. So in DTC, I told you first thing is that estimating flux as well as torque through three-phase system transfer to two-phase rotating frame. So that we can see here. Now VABC is transferred to DQ, VD, VQ, and IABC transferred to IB, IQ. So this is a transformation you can find inside that one. VABC, and this VABC VQ will result VQ minus IQR, VQ minus IQR. That integration is flux. Flux is nothing but always V minus IR, integration of V minus IR. So that is 5QS. Okay. Now this is 5QS. What would be this one? VD minus I into IDS into R. So that is nothing but 5DS, 5QS, 5DS. And you have IQS, IDS. So if you see the see here, and you see this equation, 5DS, IQS, 5QS, IDS. So okay, this is the equation that the torque is producing. They have estimated the torque here. So that products and IQS minus this one will produce the torque. So once the torque is produced, okay, once the torque is okay here, once the torque has been calculated, torque and flux has been calculated, okay, now the torque reference is going to come. The actual torque that has been estimated now, okay, will be processed and control IQS. IQS can be controlled by controlling VQS. Okay, and this is given by the AB transformation. Again, inverse transformations will be taken care, and here you can find sector identification. So once the angle, based on the angle, the entire 360 degree is divided into 6 sectors, and based on the sector you are going to give the switching pulses, switching time, and those pulses are given to the inverter. That is about the DTC. What do? We'll just run and see the DTC. And what did we say about TTC? What is the key drawback of the DTC? It's the torque ripple, but accurate torque can be controlled. So whatever the torque that you want, dynamics are very fast. However, torque ripple and everything will be there. Let us run and see this mod. you can find your transient. You can find whenever there is a change, there is a slight disturbance happening. However, we are getting the torque control as well as speed control. Inner loop is also controlled very well. Now we can take an example for the FOC. You can see AC3 is an example for FOC, so field oriented control. So here it will be flux estimator and everything will be there. Okay. So this is FOC controller. So IDS calculation and then IQS calculation, ID and IQS calculation. This is IQ and this is ID calculation through flux. From the required flux, you are going to estimate the values. FOC. See, let us run and see. You can see in FOC how accurately it's going to be controlled. So which is very important in case of certain applications, high performance applications such as EV or traction. So FOC is one of the good dynamics we can see. On a concluding note, let's have overview of the lecture. What we have discussed on this. So we have discussed about scalar and vector control of induction motor drive. So we understood what is meant by scalar control. Scalar control is nothing but related to only magnitude control of any variables. And we have seen what is voltage control, what is frequency control, and what is V/F control. And we understood that scalar control is simple and it can be very suitable for low performance drive, and it's suitable for fans, pumps, and application. Not suitable for very high performance drives, and the dynamics are very sluggish. So that's what we have seen. And we understood that vector control is related to the space vectors, either current, flux, or voltage, where not only with respect to magnitude but also with position is where as we take them as a vectors. We understood that three-phase system to two-phase quadrature conversion, and we understood what is meant by DTC, direct torque control, and field oriented controls. We have seen that vector control is suitable for high performance and good dynamics application. So applications such as EV, traction demand very high performance. And we have discussed that torque can be controlled similar to like a DC motor, torque was to flux and current. In this case, it will be vectored flux and vector current. That's what we are seeing in vector control. And finally, we had a comparison between scalar and vector control, and we have seen few simulation examples using MATLAB. So this was the content of the entire lecture. Thank you all. But if you have any queries regarding this lecture, please do contact me. Thank you.